in this advanced methods section, we're going to talk about Bayesian belief networks, support vector machines, and artificial neural network. We have in iSchool, we have a class on Bayesian inference, and we also have a separate class for artificial neural networks. So in this class, given the time limitation, we cannot cover a lot of them, a lot of details, but we will cover the basics concepts that would allow you to maybe read on your own and study new development in those areas. So learning objectives. For Bayesian belief network, the key idea is to know that this network allows you to make any inference. The key technical challenging is how to make inference efficiently. For support vector machines, the key idea is to understand kernel trick. And this kernel is different from kernel density estimation. So don't get them confused. For artificial neural network, we want you to understand the training process is different from a typical other classic training process for other classic machine learning methods, and also the back propagation concept and why it could be a problem in training a neural network. Okay, I borrowed lots of slides from people. Andrew Moore's support vector machine slides made great sense, and I love his example, so I just borrowed them. So for Bayesian belief networks, we will first to quickly recap the basic probability theory, and then we'll look at its representation and how does it do inference. About how to learn and construct such a belief network, I think you can probably learn it in the Bayesian inference class. We here only going to provide a little intuition. We know conditional probability, so chain rules and all that. Those should all be familiar to you, right? This conditional probability equals the joint probability by this condition, divided by this condition. Joint probability production rule can be directly derived from here. We take this to this side and put this back. So we have the joint probability of xy is the probability of y occurs times the probability when y occurs, x also occur, right? So this is the intuitive reading of this joint probability. The chain rule applies when you have lots of variables and you want to find the joint probability of all those variables co-occur. So the idea again is apply this basic rule here, saying that, okay, what's the probability for x1 occur times the probability when x1 occurs, x2 occur, times the probability when x1 and 2 occurs, x3 occur. So you can chain it down to when x occurs, when x to x sub n minus 1 occurs, what's the probability for xn to occur? And there is a short way to write the whole thing, and we're going to actually use this in today's lecture. We'll come back to this, the chain rule joint probability. And we also know that if xy are independent, then their joint probability has to be their marginal product of their marginal probability. So there's nothing to do, x has nothing to do with y. Then they co-occur should be the probability of they occur individually at the same time. If xy are conditional independent, given z, again, this to here, if they're conditional independent, given z, they are independent. Therefore, their joint probability has to be their separate or marginal probability given z. Okay, so those are the things we're going to actually use. To compute joint probability, because when we do the Bayesian belief network, we need to know this in order to understand how that network actually can do all those inferences. So I thought we need to have a little review here. So this represents a joint distribution. Two variables occur at the same time. And this represents one marginal distribution where the probability for x occur is the sum of the probability for x and all those y's or different y's, combined probability of x occurs with different y's. So for example, here we have the weather, temperature and weather and probability. The probability for hot and sun to occur is 0.4 and all the others. If we want to find the marginal probability for PE, the temperature, we're simply going to sum out W. So this is the sum for hot, 0.5. This is the cold, sum out sun and rain, 0.5. Okay, so we do the same if we want to find out the marginal distribution for weather. We have sun and rain. So for sun, we pick out sun and then some temperature out. We have 0.4 and 0.2. Therefore, our sun probability is 0.6. Okay, so the key idea to remember is we want to, if we know the joint distribution, in order to find the marginal distribution, our method is to summing out the other variable. When we want to find T, we're summing out W. Conditional distribution. Here, if we know the joint distribution, we can easily find the conditional distribution. So we want to say, when temperature is cold, what's the chance for sun or rain to appear? In order to find this, what we do, we first find C. Where is C? Cold, right? So the condition match our need. We take this out, so cold, and then we normalize this P. So that's probability. Some of the probability have to be 1. So after we normalize it, we have some with probability 0.4, rain probability 0.6. Okay. So this is how we, from joint distribution, find the conditional distribution. So what you see here is when you have joint distribution, you can find any conditional distribution. When you have joint distribution, you can find any marginal distribution. Okay, those are the key points.